Eğer ki hayatımızda hiç eğer olmasaydı nasıl olurdu? Size şöyle söyleyeyim. Her şey daha az parlak, daha az yeşil olurdu ve daha az parlak yeşil. Çünkü eğerler ormanların derinliklerinde tek bir kibritle devrimlerin kıvılcımını ateşler. Eğerler Nobel ve Guggenheim'ın aklına takılır ve o kodu bu kodu çözerler. Eğerlerle içinizden haykırmak gelir. Eğerler bariyerleri kırarlar. Asla yalnız yürümezler ve aşırı bulaşıcıdırlar. Eğerler aşikardır ve son anda golü atarlar. Eğerler günü umursamazlar, robotlarla bile konuşabilirler. Karşı takım soluklanırken oynamaya durmadan devam ederler. Sadece basit bir kelime öyle mi? Hayır. Eğerler asla uyumazlar, hep daha fazla çaba gösterirler. Eğerler bakar, araştırır ve en beklenmedik zamanda ortaya çıkarlar. Eğerler klonlanarak çoğalırlar. Acaba gerçekten yapabilir misin? Yaptın bile. Eğerler aklınıza girmeye çalışan güler yüzlü şakacılardır. Eğerler kapıları açarlar, asla kaybetmeyeceklerini bilirler. Ve biraz gün ışığına her zaman hazırdırlar. Her şey bir eğerle başlar. Çünkü eğerler ne zaman dönüşür, ne zamanlarsa şimdi. Ve şimdi nasıla dönüşür. Nasılsa asıl. Eğerler bakış açınızı değiştirir. Eğerler oyunu değiştirir. Eğerler dünyayı değiştirir. Biliyoruz. Çünkü biz eğerlerle çalışıyoruz. Yakın Doğu Üniversitesi.
Good morning, good afternoon, good evening, wherever you are in the world. It gives me a great privilege to chair the keynote session of Professor Braja Das' keynote lecture, which will be delivered by Professor Halit Supan. The lecture's supposed to be delivered here, but as you know, during these hard times, unfortunately, we have to go virtual or online. Therefore, he sent us a video recorded presentation, and we are going to watch it together. Professor Das came to our university 21 years ago, and since then he came 5 times, and he is with us in all 5 conferences, whether in person or with his keynotes, and is the only person which he has in every conference a keynote. And all keynotes are very good keynotes. I could say all of them are chapter of a book, and this keynote as well is a chapter of a book. So I hope you will enjoy it, and every day we are learning from Professor Das, and we are teaching our students everywhere in the world. And in this conference, I think Professor Das is going to give us more opportunity to tell all our students. So now I introduce Professor Halit Supan from Florida University to deliver the keynote of Professor Das.
foundation, and the ratio df over b is less. Good morning. Greetings from Florida. I am Professor Khaled Sobhan from Florida Atlantic University. We are located in Boca Raton, Florida, which is about 45 minutes north of Miami. Thank you very much for inviting me to give this keynote presentation. I'm giving this presentation on behalf of Professor Braja Das from California State University. I'd like to acknowledge our co-authors, Professor Patra and Professor Behera from National Institute of Technology in India, and Professor Javid Atalar from Near East University in North Cyprus, Nicosia. Looking at the picture on the left, I really wanted to be physically there in North Cyprus. The picture looks very beautiful, and I really look forward to it. But we have to keep adapting to the new and changing circumstances, the new world order, and hopefully everything will be normalized very soon. Our topic today is about the bearing capacity of shallow foundation, which is generally it's accepted that the shallow foundation is defined as a foundation with a width B located at a depth of df, depth of foundation, and the ratio df over b is less than equal to 1. And we are focusing on strip foundation and three types of specific loading conditions, such as the eccentric loading, inclined loading, and eccentrically inclined loading. As we all know, back in 1943, Carl Terzaghi came up with his landmark bearing capacity theory. Since then, many researchers, many scholars throughout the world have provided some modifications and extensions to that classic Terzaghi bearing capacity theory. So our paper is a review paper. The literature is very vast. Again, we just focus on these three types of loading conditions. Let's move on. Terzaghi made a very important statement in 1943, and it says that the problems of soil mechanics may be divided into two principal groups: the stability problem and the elasticity problem. So here today we are dealing with that stability problem, which is bearing capacity failure. But the other very important aspect is the settlement, whether the settlement will be excessive in that shallow foundation, and that is considered as an elasticity problem. So these two combined aspects of foundation design constitutes really the essence of geotechnical engineering. Our presentation outline, we divided into 4 parts. Part A is the strip foundation subject to centric loading. Part B is subjected to vertical eccentric loading, and part C is inclined loading, and part D is eccentrically inclined loading. Let's talk about part A, ultimate bearing capacity of strip foundation for centric loading. Terzaghi proposed this failure surface. As you can see, and as we know, in this approach, we assume that the foundation is located at a depth of df, and the soil above the level of df is approximated by the surcharge. which is given by Q equals to gamma times dF, gamma being the unit weight of the soil. Terzaghis theory deals with the C-phi soil. So cohesion is C and the friction angle for the soil is phi. There are three zones. One is that elastic zone A, B, C. Then there's this radial shear zone, and then the passive zone, B, F, and G. Terzaghi assumed that the angle alpha is approximately equal to the friction angle phi. So below is the Terzaghi bearing capacity theory, and since we are dealing with granular soil, so the first term will cancel, and this equation will be shortened. The first major extension or modification to the theory was proposed by Meyer in 1951, about 8 years later, and he proposed failure surface, which looks like that, and it still has the elastic zone, and it also has this equivalent free surface called BE, on which there's a normal stress PO and a mobilized shear resistant S0, SO, and he assumed the angle, which Terzaghi assumed to be alpha, he assumed it to be 45 plus phi over 2. And the theory is, the bearing capacity theory is given below, right here. And some of the terms are defined as follows. The PO is normal stress on the equivalent free surface, and M is mobilization, the degree of mobilization, and C plus P0 tangent phi multiplied by M. M varies from 0 to 1. The angle BAC and ABC in the triangular elastic zone is 45 plus phi over 2, in contrast to phi as assumed by Terzaghi. And the bearing capacity factors NC and Q and N gamma are functions of phi, M, and beta. I forgot to mention that for the Terzaghi, NC and Q and N gamma factors, as we know, are dependent on the friction angle phi, and generally they're available in tabular forms. So for Meyerhoff's bearing capacity factors, which are dependent on phi, the mobilization factor M, and beta, where beta is the angle between the equivalent free surface BE with the horizontal. So that angle over here is beta. And the factors in Q and N gamma dependent on beta and M and soil friction angle are given in these two graphs. A special case of Meyerhoff 1951 solution will look similar to what Terzaghi's theory looked like. Again, the angle alpha has changed to 45 plus phi over 2. And back where theta was, theta is now 90 degrees and M equals to 0. Under those conditions, the soil above the level of the foundation is again replaced by, or presented or approximated by, gamma times dF, and which is equal to the normal stress PO. For granular soils, the C term cancels out. So this is the ultimate bearing capacity, and the bearing capacity factors in Q and N gamma are functions of phi. Although the bearing capacity expression and NQ over the years did not change, many researchers proposed different types of relationships for the factor n gamma. And some of those n gamma relationships are as follows. And it just depends on the condition and the assumptions of the theoretical development. And these references are available in our paper. At the end of the paper, in the references, the details are available. Then the depth factors were incorporated just to account for the approximation that happened by replacing the soil located above the bottom of the foundation by the distributed load, the surcharge load Q, which is equal to gamma dF. The depth factors were introduced, dQ and d gamma. And Meyer in 1963 proposed depth factors in this fashion. Again, it's a function of the dF over B and also the phi. And other well-known depth factor was given by Hansen in this manner. Again, function of phi and dF over B, and d gamma is equal to 1. So that's pretty much about part A, where the strip foundation is under centric loading and in granular soils. So those are the two most well-known theory and theoretical developments, and we saw some modifications of some new over the years since 1960s, basically, the proposed new relationships for the n gamma factor. That's pretty much it for part A. Part B, let's move on to part B. It says foundation on granular soil subject to vertical but eccentric loading. An extremely well-known solution was given by Meyer in 1953. It's called the Meyer's effective area method. As you can see on the right-hand side, this is the total width B, and then there's an effective width B prime, which is given by B minus 2 times E. E being the eccentricity, we're looking at the plan view, we're looking at the eccentricity E of the loading, and it is vertical loading. So B minus 2E is the effective width B prime. So QU prime is the ultimate load per unit area. Notice that the B, that equation, Meyer's equation, incorporating the depth factors, is now incorporating B prime instead of B. And load in that effective area will be given by QU, capital QU. And notice that the B term, the depth factor, so if you recall the relationship in the equations of the depth factor, the B term in the depth factor should be replaced by B prime. So this is how Meyer's effective area method to estimate the load bearing capacity of the foundation when it is subjected to a vertical eccentric loading. Now, this one is based on that effective area, effective width, but on the average, we sometimes need to understand what is the average ultimate load per unit area. So that QU prime that we just saw is the hypothetical ultimate load per unit area based on a theory, with the width B prime being B minus 2E. So the average ultimate load per unit area, which is given with this notation, QE within parenthesis E. So it means that it's QU and there is eccentricity but it's an average ultimate load is given by this equation, and you can see that this is the B prime. So the B prime over B is used as a ratio to estimate QUE in an average sense, which is the average ultimate load per unit area. Prakash and Saran, 1971, so almost 20 years later, they postulated theory on strip foundation on sea and fee soil. So both cohesion and friction angle are present. And they define the failure zones. So you see zone 1, zone 2, and zone 3. It still has that A, B, C, the elastic zone, radial shear zone, and then the ranking passive zone. So kind of similar in concept. The foundation is at the depth of DF, depth of foundation, depth of the footing. And you can see the load uppercase Q subscript U. It is vertical at an eccentricity of E. Considering the equilibrium of the elastic wedge A, B, and C, and depending on that eccentricity, Bx1 is the contact width of the foundation and the soil. So here is B, and then here is Bx1, and x1 varies with E over B. So with the eccentricity, the x1 fraction varies according to figure C. So considering when you consider the equilibrium of that elastic wedge ABC, you need to take into account the variation of the width with x1 because it depends on the eccentricity. And based on that, Prakash and Saran postulated this theory for the ultimate load per unit length of the foundation of width B. Again, remember we are dealing with strip footing. So per unit length of that strip footing is given by this equation where PP and PM, and you can see that here is PP and here is PM on that passive zone. So both relates to the passive forces per unit length of the wedge. These are passive forces per unit length of the wedge along the wedge faces BC and AC respectively. Phi is the soil friction angle, phi sub m is the mobilized soil friction angle, and which is less than equal to phi. And C alpha, CA and C prime A are the adhesion in those forces BC, in those faces BC and CA. So you can see CA prime and CA, and they're given by these ratios. The angle size are given here, psi 1 and psi 2. So this is and mobilization factor is less than equal to 1, and C is the unit cohesion. So this is what Prakash and Saran in 1975 postulated on the ultimate load per unit length of the foundation of width B. Again, we are in part B, so we are dealing with load eccentricity. So therefore, the average ultimate load per unit area, so which is our actually classic definition of bearing capacity, will be equal to this, and which can be expressed in the form of similar to Terzaghi's original theory. It can be expressed in this fashion. Again, we don't have the C term because we're dealing with the granular soils. And you notice that the bearing capacity factors are now called N gamma E. E is for the eccentric loading. says here the bearing capacity factors for eccentrically loaded but vertical loading continuous foundation. So ultimately the equation looks like this. And the bearing capacity factors NQE and N gamma E, the function of E over B and the soil friction angle. So that is what was proposed by Prakash and Saran almost 20 years after Meyer's effective area theory. Then there was another theory postulated by Purakayasta and Char in 1977. It's called, in general, it's called the reduction factor method. Many other investigators have looked into the reduction factor method. And they actually performed a stability analysis of steep foundation on sand using the famous Yambu method of slices for slope stability analysis. And they proposed the reduction factor as follows, which is 1 minus the reduction factor is 1 minus QU E over QU. Remember, QU is the ultimate bearing capacity for the control case where there is no eccentricity. And they defined RK, the reduction factor, in this fashion. Of course, it depends on the eccentricity. And A and K, the parameters A and K depends on the embedment ratio. And they provided the variation of A and K with respect to the DF over B, the embedment ratio. So from the previous equations, we are aiming to estimate QUE in terms of the reduction factor. It takes this form. Okay. And for any eccentricity, and if you know the DF over B, then you can estimate the ultimate bearing capacity for the eccentrically loaded foundation. Since C equals to 0 for granular soil, the QU, gamma DF DQ, remember the equation, bearing capacity equation, incorporating the depth factors, looks like this. And there was a comparison made between this reduction factor that was proposed by Purakayasta and Char in 1977. A comparison was made between their reduction factor, because reduction factor is a convenient way for estimating the bearing capacity of eccentrically loaded foundation once RK can be ascertained, right? So there's a comparison made between what they proposed and based on what was experimentally observed. You can see this chart shows the variation of RK with E over B, the eccentricity ratio. And the Meyer's effective area theory was also expressed in terms of this reduction factor. And you can see that if you recall that this is the Purakayasta and Char definition of reduction factor. And we can bring in the Meyer's effective area method right here. And when you simplify it, it looks like this. So according to Meyer's effective area theory, RK looks like this. It's only a function of E over B. So based on that, for various values of E over B, Meyer's the dotted line is by Meyer's effective area method. And all these symbols relate to experimentally observed RK value. And then by Purakayasta and Char, the values from this table which gives you the variation of A and K with respect to dF over B, what would be the reduction factor. You can see there's very reasonable agreement between Meyer's theory, the Surcharge method, and some experimentally observed data. So where are we now? We have established that the reduction factor method is a viable method. It nicely agrees with the experimental observations by various investigators, and at least and very nicely the Meyer's effective area theory developed for the vertically eccentrically loaded foundation. For that case, it nicely agrees with the Meyer's effective area theory. Okay. And this comparison was made based on surface foundations where dF over B equal to 0. Okay. Our co-authors, Patra, Behra, and Professor Das, in 2012, they published results from quite an extensive series of laboratory investigations for both medium dense sand and dense and medium dense sand with dF over V varying between 0 to 1 and E over B eccentricity ratio varying from 0 to 0.15. So these results, we will discuss these results later also. But based on their experimental observations, they found that the QUE, because that is the goal for this part, the ultimate bearing capacity for eccentrically loaded foundation is equal to QU times this factor, approximately equal to this factor, which incorporates the eccentricity ratio. So it looks like a nice approximation and to estimate the eccentrically loaded, the bearing capacity of eccentrically loaded foundation. From the same group of researchers, quite relatively recently in 2013, they also looked at the load settlement relationship for eccentrically loaded foundations. So our goal is in this paper is mostly focused on the bearing capacity, but this is a very related item. Recalling that Terzaghez's landmark statement that both bearing capacity and settlement, they go hand in hand. So based on the experimental investigation, they looked at the average settlement along the center line of an eccentrically loaded steep foundation. So along the center line of the foundation. SU is the average settlement along the center line at any given dF over B. And SU prime is the settlement at dF, so it's like a surface foundation and with no eccentricity. Okay, so a surface foundation is the settlement of a surface foundation with no eccentricity, and this is the settlement, average settlement along the center line of the foundation at any given dF over B. So on the right-hand side of the equation, you can see dF over B, and right-hand side of the equation, you can see the eccentricity ratio. And SU prime is that average the settlement of the foundation of the surface footing at no eccentricity. So if we have an estimate of SU prime, then we can get to the settlement, average settlement along the center line of this eccentrically loaded foundation at a given df over b. To estimate SU prime, estimating SU prime over b, De Beer in 1967 developed this chart, the solid lines, for a circular foundation. And this is the variation of the parameter that we are trying to estimate, SU prime over B in percentage, and the variation with gamma B over P0, which is the atmospheric pressure, the normalizing factor. So Patra et al. Looked at the strip foundation, not circular. And those are these dotted lines. They provided the estimate of the SU prime over B based on their work for two types of equation when gamma B over P0 ends at 0.025 up to that. So it compares reasonably well with the De Beer 1967 graphs. And they also, Patra et al. Also developed empirical correlations. What happens with gamma B over PA when what happens to SU prime over B when gamma B over PA exceeds 0.025. So again, either way, if SU prime is estimated, then you can go back to this equation. And for any DF over B and eccentricity ratio, you can estimate the average settlement along the center line of this vertically eccentrically loaded foundation. Normally, in a live audience, we would ask for any question from the audience. So I don't know how this recorded lecture will be presented. If you have any question, I'm talking to the participants and the audience. If you have any question, please feel free to contact us. Again, the details of all these are presented in our paper, which will be published by the conference. So we are in part C. We finished centric loading. We finished eccentrically loaded foundation, but that loading was vertical. Now we are, for the time being, not looking at eccentricity, but we are looking at inclined loading. Okay, and look at the development and the extension of Terzaghi's theory and Meyer's theory to incorporate inclined loading. 1953, Meyer's, right after the 1951 effective area method, he postulated this failure surface for inclined loading. So let's look at this one. So QUI is the bearing capacity or bearing capacity for that inclined load. The load inclination is alpha with the particle. The width of the foundation is again B, and the foundation is located at the depth of DF. You have that elastic zone, very similar to what Meyer's theory showed before for eccentrically loaded foundation. And you have the shear zone. So ABC is the elastic zone, BCD is the radial shear zone, and BDE is the mixed shear zone. And similar to the eccentrically loaded foundation, you have the normal stress PO and the mobilized shear stress SO along the plane, equivalent free plane BE, and alpha is the load inclination angle. So Meyer expressed his bearing capacity formula in the following manner. So QUI means incline, and the vertical component will be equal to QUI cosine alpha, and it's expressed in this way. And QN and gamma are the bearing capacity factors for incline loading. Gamma is the unit weight of soil, and QUI is the average ultimate incline load per unit area. Average ultimate incline load per unit area, the average bearing capacity. There's no eccentricity, and QUIV is the vertical component of QUI. And the bearing capacity factors will be different because it's incline loading. And Meyer represented the NQ and N gamma in this way, where PP gamma minimum, where you will see from the failure surface, PP gamma minimum is the minimum passive force per unit length of the foundation acting on phase BC at an angle phi. So it's not shown here in this diagram. And so the plane BC is right here. So the ppm will be right here. Okay. And of course, it is, so you need to know all these angles. And this can be, of course, expressed in the usual manner, again, following the Terzaghis landmark theory along the same format, along the same line. And it is expressed like this. In 1963, he expressed his bearing capacity for incline loading, the vertical component of the ultimate bearing capacity. Given in this format, the NQ and N gamma are the bearing capacity factors, DQ and D gamma are the depth factors, and he defined the inclination factors in this manner. So these are the Meyer's inclination factors. So again, we come back to the form that we are familiar with, and with modifications made into the original theory. In this case, along with the depth factor, which Meyer postulated, he incorporated the inclination factors. Variations of bearing capacity factor N gamma Q with alpha for df b over 0 from 0 to 1. So he postulated a second format of this, considering that if it is a surface foundation, so variation from 0, df over b from 0 to 1, and he expressed this bearing capacity factor as, he expressed it as N gamma Q, and this shows the surface foundation and varying up to 1, so it's the definition of shallow foundation, and it varies with the load inclination factor, and these are the friction angles. So for these specific conditions, for surface footing, and when df over b is 1, for these specific conditions, he expressed his the vertical component of the ultimate bearing capacity with load inclination. He expressed it in this simple form, half gamma b n gamma q, with n gamma q retrieved from this chart. So here is one solution. Here is the other sort of classical solution, and with the incorporation of the inclination factors. There's some theoretical, purely theoretical, from the basis of theoretical development. Dubrova, worth mentioning in 1973, with centric incline load, he postulated this equation. 2Q and Q, the vertical component of the ultimate bearing capacity with inclined centric loading, which is expressed in this way. Alpha is that load inclination angle, and the bearing capacity factors NQ star and N gamma star varies with the soil friction angle. So from purely theoretical considerations. And of course, there are some empirical observations. And again, just want to say that this review is not meant to be comprehensive, but this review paper points out the significant, noteworthy developments. So there may be others, but these two are noteworthy. One is by Maas and Wise, 1973. Q is the ultimate bearing capacity with centric vertical loading, and QUIV is the vertical component of the inclined centric loading. And you can see that it's only dependent, this ratio is only dependent on the load inclination angle. And assuming QU is estimated, and these two must be at similar DF, at similar values of DF over V. So quite a simple formula developed through empirical correlations. I always tell my students that anything that ever changed the world was actually pretty simple. If you have a very long equation, chances are it will not be adopted by the practicing community. And it is purely, again, my personal opinion. Okay? And of course, Patra et al., you know, that reference that we are referring to quite frequently, based on the experimental model tests at any given DF over B, they postulated this, you know, based on their empirical observations. And they mentioned that it provides a closure agreement to the Meyer of solutions. Okay. Again, on the right-hand side, QU has the same meaning. On the right-hand side, it varies with the soil friction angle, DF over B, and the load inclination. Now we are at part D, which is the strip foundation subjected to eccentrically inclined loading. There are a few more. I just have to mention that in our paper, hopefully some members of the audience would be interested in this topic and would read that paper. That paper does include few more references and have discussed briefly, but the ones that I'm putting on this presentation are the ones that I thought within this limited time was worth mentioning. So part D, strip foundation subjected to eccentrically inclined loading. So it's not only inclined, but also the loading is eccentric. So there are two cases that can happen. One is called the partially compensated case. Another one is called the reinforced case. In the partially compensated case, the line of application of the foundation is inclined toward the center line of the foundation. And you can see that is the case here. And as opposed to the reinforced case, where the line of application is moving away, is inclined away from the center line of the foundation. This is the center line of the foundation. This is the eccentricity E. Vast majority of the literature deals with the partially compensated case, and there are very limited information on the reinforced case. These definitions were developed by Parloff and Barron. I believe it's a textbook published in 1976. So Q, the big Q, the capital Q subscript U parenthesis EI is the ultimate load per unit length of the strip footing. considering that there is load eccentricity and also there is load inclination. Again, for the Meyer of 1963 effective area method, incorporating both the inclination factor and the depth factor. This is the Meyer of effective area method to deal with the inclination and the eccentricity. Q prime U EI dash V. Q prime U is the ultimate bearing capacity effective area method. We can see B prime here, B prime being B minus 2E. And then you have the vertical component of that. So here is this equation. Based on the previous development, it is expressed this way. The D gamma, I gamma, IQ, DQ are all based on the original Meyer of developments that we already discussed and the equations that we already discussed. So this is the effective area method by Meyer. So we have looked at Meyer's theory for centric loading, and then for eccentric loading, and then inclined loading, and now eccentrically inclined loading. Saran and Agarwal in 1991, they did pure theoretical analysis, and they postulated this, where NQEI and gamma EI are the bearing capacity factor. If alpha is equal to 0, then NQEI will just become NQE, because if there is no inclination when alpha equals to 0. And they coincide with previously we talked about the Prakash and Saran 1971 theoretical analysis. So they will, for alpha equals to 0, they will collapse into the same bearing capacity factors. There were no recommendations provided for the depth factors, how they should be calculated, and no mention of the or no recommendation of the depth factors. So they provided guidance for the, again, this is theoretical analysis. They provided guidance to determine NQEI and N gamma EI, with solid friction angle, phi, and eccentricity ratio E over B. So there's E over B, and then there is soil friction angle and the load inclination from 0 to 30 degrees. So there is guidance for NQEI and N gamma EI. I apologize that the writings are very, very small. It's a lot of graphs. I didn't want to truncate this. I could have, just to show you what it is, but just wanted to show you that in a comprehensive way, load inclination factor goes from 0 to 30 degrees. Okay, and there's eccentricity ratio and wide range of friction angles, so pretty comprehensive development for the eccentrically inclined loading. There were some numerical analysis based on finite element method. And you can see this is QU with DF over B 0. E over B has a value. Alpha normalized by phi has a value. So eccentrically inclined loading at the surface, that is QU. This is the vertical component of the limit load VL. Okay, so this is the vertical component, and you divide by B, you get the bearing capacity. And then there is this bearing, there is this factor, which is the combined inclination eccentricity factor, FIE, which was given by this based on finite element analysis. How does this compare with the previous development? We don't know. They were not reported in the literature. These are my understanding, these are independent analysis. Then some of our co-authors, the famous 2012A experimental investigations for two different relative densities, namely dense sand, medium dense sand, subjected to eccentrically inclined load. I wish I had that experimental setup. I have it in some other presentations that I have seen and I have given. I wish I could bring that experimental setup picture here. Sorry for that, and it is given in that paper. So if you're interested to know how that setup has been constructed. Based on 120 laboratory tests for ultimate bearing capacity of a strip footing that are eccentrically inclined loading. Remember, we talked about the reduction factor method. So we call it RFP because it's by Patra et al. And then that is defined this way. QU is the ultimate bearing capacity at a given dF over B, same as for QUEI. So for a given dF over B and alpha equals to 0. So this is given dF over B, alpha is equal to 0. That's the ultimate bearing capacity. And the reduction factor, this is what we are looking at, right? QUEI will be a function of the eccentricity ratio and load inclination normalized by phi, and at any given dF over B ratio. So Patra et al. Developed this empirical relation. So they experimentally determined what RFP would be, and then developed this equation. Remember Meyer's theory? So based on Meyer's theory, effective area method, RFM can be calculated using Meyer's theory. So we call it RFM. And we're saying RFM can be calculated based on Meyer's bearing capacity, depth, and inclination factors. So these are the equations that have been developed and discussed so far. RFP is based on laboratory model tests, and they can be compared, right? And it was found that RFP and RFM are within about plus minus 10 to 15%. So it's a pretty nice agreement. In the paper, we have a very extensive table. In that table, these comparisons have been shown. Okay, the calculation of Meyer's reduction factor and the experimentally obtained reduction factor by Patra et al. So we have included the table in our review paper. And here's the comparison between RFP and RFM. You can see that all these, the hollow symbols are the Patra experimental results, and the dark symbols are the Meyer points. We are plotting the reduction factor predicted by those equations and reduction factor experimental. And here's a direct comparison of RFP with RFM. And you can see that there's a pretty nice, so RFP, so by Patra, the reduction factor is slightly bigger with a R-squared coefficient of determination of 0.95, pretty good fit. And it's approximately equal to RFM. It's almost the same, so it can be ignored. So that's a pretty good agreement. So again, this is Meyer's, based on Meyer's effective area method. Based on that, you can calculate RFM and then compare with the experimental reduction factor by Patra et al. And This is a pretty nice validation of the reduction factor method, which was, if you recall, originally we talked about it by Purakasta and Chan, 1977 paper. There's very little, so far it was, as I mentioned, that most of the cases in the literature are on partially compensated case. Here we are talking about reinforced case, and very little information is available. This is the numerical analysis by Ludwig, and I apologize. My daughter was talking in the background. This is what we learned working from home. This is my home library. As you can see, all these books behind me, and I can assure you I haven't read all of those books. So I just wait them to leave me alone for a few minutes. Coming back, reinforced case. It's a numerical analysis by Lukidis et al. In 2008, based on finite element analysis. We talked about it before, but right now it's for the reinforced case, for eccentrically inclined loading. So that combined inclination eccentricity factor, FIE, so it's slightly modified here. They called it a negative case. So in the previous equation, this sign was positive. Here it's negative. And and you follow the same approach that was presented before, except for this FIE, now it's called pride. Empirical correlations, again, we are looking at the reinforced case. Almost no information is available on experimental determination of the reinforced case based on 70, except for Patra et al. 2012a. So based on 72 laboratory model tests, they proposed this formula: the ultimate bearing capacity at a given dF over B with E over B greater than 0. So there is eccentricity at a given dF over B based on 72 laboratory tests. They found this, they developed this equation. You can see on the right hand side, there is eccentricity ratio, and there is the load inclination angle alpha and the dF over B. It was found that for similar dF over B and E over B, QUEI, which is our goal for reinforced case, is slightly higher than partially compensated case. And they also developed the relationship for settlement ratio. And you can see that, again, you can see that the reinforced case divided by the partially compensated case for alpha from 5 degrees and alpha at 20 degrees, it varies from 1 to 1.4. So they looked at the dense sand. So these are the experimentally observed behavior, dense sand and medium dense sands, relative density from about 70% to 50%. And you can see the ratio of QUEI for reinforced over partially compensated for both types of sand. This is what the experimental observations look like. dF over V varied from 0 to 1. And these are the eccentricity ratios. And for similar diagrams for the settlement ratios, very interesting experimental observations and the elaborate setup that our co-authors have constructed in the National Institute of Technology in India. So we are definitely, the academic community is very grateful for their extensive series of laboratory tests that were pretty painstakingly done, and we could make use of that data for future predictions of and calibration of our models. So it's a similar trend, and this ratio, nice guideline, reinforced ratio of reinforced case to partially compensated case. So you have a nice idea about how the settlement would vary. Finally, our co-author Behera, very recently in 2018, probably this is the only case where we say it's a combined case. It's combined case means it's not eccentricity and inclination. It is about the partially compensated case and the reinforced case. And they took they took all the laboratory test results done by Patra et al. 2012A, almost like 200 laboratory model tests, and developed this reduction factor. And on the top is QU, and it has DF over B, E over B, alpha over Phi, and LA, which is a new term. LA is called a load arrangement factor, divided by kind of like a control case at the similar DF over B, and the E over no eccentricity, no load inclination, and the load arrangement factor of 0. So we know this. At least we want to claim that we know this from various means. And this is the right-hand side. So the new item LA is called the load arrangement factor. And this is how they combine the partially compensated case and the reinforced case. Pretty novel work. And it will be -1 if it's partially compensated. Here is LA. And it will be 0 for centric inclined, and eccentric vertical loading. And then it will be 1. It goes from -1 to +1 to the reinforced case. So pretty novel approach and pretty comprehensive. And that was recently published in 2018. So here's some conclusions. I was not keeping track of the time. I'm recording it at my home, so nobody was alerting me about the time, but I'll be brief now. So we have done a review of the developments in the area of ultimate bearing capacity of shallow strip foundations on granular soil due to these conditions: vertical eccentric loading, centric inclined loading, and eccentrically inclined loading. Next, based on the review, it appears that Meyer's bearing capacity theory, incorporating the depth and inclination factors, are probably still the best approach. And any new developments are actually, compared with the Meyer's approach. For foundations subjected to vertical eccentric load, method proposed by Patra et al. Provided a reasonably good estimate of the ultimate bearing capacity for the vertical eccentric loading. And it was compared with other methods. There was a novel procedure presented by Patra for the average settlement of a foundation under an allowable eccentric vertical load. Okay, but it says we want to make a statement that the estimated settlement should be considered as a first approximation only, but the approach was, in our opinion, pretty novel. And then the bearing capacity factors are subjected to eccentrically inclined load from ultimate bearing capacity of centrally loaded foundations compares reasonably well with Meyer's theory. Again, as I mentioned, that Meyer's theory appears to be the best, still the best, and any new developments are compared back to Meyer's prediction. And Patra et al. Findings, the empirical findings, correlate reasonably well. Finally, our co-author Behera et al. In the recently published paper developed, in my opinion, it is a novel approach where the partially compensated case and the reinforced case were combined, and it was actually compared with several of the available methods, including Meyer's method, and it was found that it compares reasonably well with other similar existing theories. So that concludes my presentation. Hope you enjoyed it. There's no scope right now to interact with you lively, the audience, but if you have questions, I'm sure there will be a way to communicate to us, to any of the authors, and certainly for our lead author, Professor Das. It has been a pleasure giving this presentation. Have a nice evening. Thank you.
Yes, we thank Professor Das, Professor Sopan, and Professor Patra and Dr. Behara about this wonderful work. And I hope you enjoyed it. As Professor Supan says, if you have any questions, please send them to us, and we will send it to Dr. Das, Professor Das, and Professor Supan. I am proud actually to listen again to Professor Das's keynote, and I hope you enjoyed it as much as I did. And I would like to close this session. And for the next session, it will be Chairperson Professor Askar and the keynote lecture of Professor Shin. Thank you for joining us for the first keynote lecture of Friday, 1st July 2022. Thank you.
Thank you, Professor Javid Atalar, for giving to me speech. The first, I congratulate organizing committee of Fifth International Conference of New Developments in Soil Mechanics and Geotechnical Engineering, and also personally Professor Javid Atalar, and also administration of Near East University in Cyprus for organizing of very important forum for our geotechnical community. And now I want to introduce my friend, great Professor Yeonchul Shin from Incheon National University. Professor Yeonchul Shin is currently Emeritus Professor of Incheon National University. He is born in March 1st, 1955, same age with me, and graduated from Chunbuk National University in Korea. He obtained a master degree from University of Colorado at Boulder of United States, 1987, and PhD degree in engineering science from Department of Civil and Environmental Engineering, Southern Illinois University at Carbondale, United States in May 1994, under scientific supervision of famous Professor Brian Das. After that, he 20 years work in geotechnical engineering area in Incheon National University. So already I told you he is now the emeritus professor. Professor Yeonchul Shin was vice president of International Society for Soil Mechanics and Geotechnical Engineering for Asia 2017-2022. Professor Shin already prepared under his auspices and supervision 52 PhD students and 156 master students. It is very big contributions for not only for Incheon National University and also for South Korea. He also adjunct professor of PhD program of Geotechnical Institute of Eurasian National University, it's my university in Nur-Sultan, Kazakhstan, since 2006. He already organized several international conferences in Korea and disaster prevention reductions, and the topic also related with the cold region development, smart city, and another topics. He participated participated in international conferences like as keynote lecture, invited lecture, and special lecturer in 5 continents in the world. He published 5 books on geotechnical engineering and geoenvironmental and civil engineering related subjects, and also more than 120 journal papers and 170 conferences papers. Minister of Education and Science and also Minister of Transportation Kazakhstan recently presented him in achievement medals for his appreciations for preparation of PhD students for our university, for Kazakhstan University, and also for consulting for high road projects between shootings in Astana. It is very international projects, very important for our country. He also received the 2008 Achievement Award presented by International Geosynthetic Societies. He was director of Creative Educational Program for Future City Design, which supported by Ministry of Education of Korea. So this project was about $9 million for 4 years. So he also received Gersivanov Medal. It's a very prestigious medal from Russian Geotechnical Society in 2021 in Moscow, and also awarded honorary doctorate degree from St. Petersburg State University of Architecture and Civil Engineering. It is the oldest university in the Russian Federation, also in 2021. So his topic today, static and dynamic behavior of shallow foundations reinforced by honey cell modular blocks. So please, Professor Shin.
Thank you, Professor Oscar and Professor Javier for your kind introduction. I think Professor Oscar is one of the persons who knows me best in the world. I think he's a well-known scholar, and he is previous vice president of ICSMG for Asian region. Previous, the Professor Dowata. Today I'll talk about the shallow foundation problem with the reinforced by the hollow concrete block. I think that many countries in the world that shallow foundation sometimes is subjected to the static, sometimes to the dynamic loading. So in the few days ago, there was a big earthquake strike to the Afghanistan, and more than 1,000 people died because of the foundation system, and the building construction is not strong enough against the earthquake, the striking force. So I'll talk about this. We did work now about 2 years regarding on this subject, where the South Korea is located in the far eastern, northeastern area here, and we have the Korean Peninsula. Unfortunately, Korean Peninsula is divided by 2, and the northern part North Korea, southern part is South Korea, like Cyprus, North Cyprus and South Cyprus. It takes about 16 hours to come to the Nicosia by Istanbul, Turkey. I think it's unfortunately we cannot travel, freely to the Nicosia due to the, very expensive airfare and also the COVID-19. So I've been there, 2002 and 2012. I think 3 or 4 times I've been there already. And the beautiful city and the beautiful island of the Cyprus. This is a view of the where I am now. I'm located in the here, Incheon National University. So enter this land. It's reclaimed from the sea. They used down. This is another way.
Professor Shin,
Yes.
We couldn't see your slide at the beginning. We just saw the first page of your slide. Is it possible to go again?
Oh.
Can you see your slide now? Can you monitor it, or can we help you?
Yeah,
Can you upload your slide, please?
Oh.
Your presentation.
you cannot see. Oh,
Now,
sorry.
because we
try
can
again.
see you, not your slide. Abdullah slide'ını koyabilir misin? Profesörün biraz önce vardı. Şimdi yükletmek istiyoruz da.
Evet.
Okay. But you did upload it a bit earlier, Professor Shin.
Hmm?
You uploaded we saw your presentation.
오케이. 프레젠테이션을 가리잖아, 채널. Okay.
Sir, you need to go to the
Can you
share.
see it? Can you
We
see
can
the
see
screen?
Yes, it's okay now.
It's coming now.
Perfect.
It's okay. We can
Lovely.
see it.
Wow.
Now it's okay?
Now it's okay. Is the first
Oh.
page? Yes.
All right. So,
Continue.
good morning. I'll discuss about the static and dynamic behavior of shallow foundation, reinforced by the honey cell modular block. There is a hollow concrete modular block. We haven't done research work in the past 2 years, and now South Korea is located in the far eastern part, northeastern part, and Korea is a peninsula. But unfortunately, Korean peninsula is divided by two, and the North Korea in northern part. South Korea we are in the southern part, and takes about 16 hours to reach to the Nicosia via Istanbul. I think it's a long journey to be there. I was there maybe 3 or 4 times in the past. Yes.
Yürümez. Şey yapayım. Professor Shin,
Yes.
are you going to the next one or not yet? Can you go to the next slide?
Yeah, I have it.
No, we don't see it. It's the
Oh.
same.
Oh,
Yardımcı olabilir misin?
Altındasın işte.
just a minute.
Can you go to the second page?
Yeah, we'll do. Just a minute.
Yani konuşurken ikinci sefer kapattı.
Now
you
we cannot see it now.
Oh,
You just need to go to the second slide by clicking the PowerPoint. Yükle olacak.
Yollasın bize de biz yardımcı olalım.
Yüklerik ya olur lan. Yollasın.
Professor Sheen,
Yes.
can you send me your slides so we can upload it here and help you
Sure. Yeah, that's right.
if you cannot do it.
Send. Okay, we'll send you my slide so you can show it
But
to
when you
me.
upload it, if you put next slide, it's going to go, but your one is not moving.
Yeah. Oh, but here, this part of the slide is moving here.
It's moving here, but we cannot see it.
Oh, okay.
Oscar, can you see it? We are not seeing it. Nobody. Munir says, tell him to use the tab promo mode.
자기한테 저걸 보내달라는데 파일을. Okay, we'll send you the file.
Did you send us your file?
No, just wait. We'll send you file.
We cannot send the file. Where? We can
아니,
send
내가
you.
저기서
So
이메일에서
It's
보내.
too big.
email?
응.
Okay, we will send you. by
We'll
email.
send you the file by email. Okay.
Okay.
Just a minute. 내가 못 들어가는 거 아니야? 내가 저기서 보낼까? I sent my file PPT to you. I sent my PPT to your
Okay.
email address.
Okay, I'm looking at my emails. I
Yeah.
haven't received it yet. Time you can try to upload it. Try to upload it to see maybe this time you can work.
Okay. Can you see it?
Okay, we can see it. Okay,
Tell me.
try to move. Go to next one.
Can you
Good,
see it?
you can go now.
Okay.
Yeah, we can see. Okay,
Number three.
okay,
Number three. Number three.
okay.
Can you
You
see
can
it?
carry on. That's okay. We
Okay.
can see.
Very good. Very
Now
good.
it's working. Thank you.
So that the slide you are now watching it is the location of Songdo here. The airport is here in the island in the Incheon, I think Yeongjong Island. So this entire land is reclaimed from the sea, and our university is located on the reclaimed land. Okay, now right hand side is land reclamation is on the way. Okay, so the Seoul is not far from here, about 30 kilometer away to the east. So content of my presentation today, introduction and the methodology and the static and dynamic laboratory model test. Particularly dynamic is more likely the shaking table test. And the result and analysis, conclusions well drawn. You see, there are plenty of soft ground. The land is consists of soft clay and also sometimes by loose sand. As you see, that location of the Incheon is along the coastal line. So we have a lot of lack of a bearing capacity problem. So we need some kind of reinforcement for shallow foundation. So we sometimes use the geogrid, sometimes we use the geosynthetics, and now we are using the hollow modular concrete block. It's now popular in practice, and we called as a honey cell. So reliability of honey cell capacity has been studied by the laboratory test, static and dynamic shaking table test, and also plate load test at the site. And the field has been successfully implemented for real structure construction site. We did have more than 400 project sites in South Korea. Why this methodology is so popular? Because of the cost effective and the very simple construction method, which gives a tremendous expanded market share in Korea. I think we'll show you all the mechanism of the soil reinforcement. This is a conception of a honey cell foundation. Foundation's shape is like this, okay? 4 blocks together manufacturing, already made concrete, okay? I think the thickness about 15 centimeter. I think up to these 4 blocks together as a one block. And at the bottom here, we are grading the virgin ground, and then we layered about 30 centimeter thickness of the crushed stone. And then we set up the honey cell modular block, hollow block, and we fill the crushed stone, and then we put in the lean concrete and also the normal foundation, shallow foundation system on the top. So this is one of example of a schematic diagram of the layout and the plan view. So this is a consequence of the construction work. This is the the view of the honey cells, and this is maybe we can construct it without excavation or scrape up of the ground surface, or we have excavation. We want to have a basement, so 1-story basement or 2-story basement. After we grading it, and then we place the crushed stone about with the thickness of about 30 centimeter, and then we compact it by the smooth fill roller. After then, by using the crane equipment, we transport this block one by one. I think it's heavy enough for people to transport this block. So need equipment. After that, we fill the crushed stone inside of the block and a little bit upper part, and then with utilizing small compactor, we just remoring and lightly compacted ground surface. I think this is the finish of the foundation system, like this. So that failure mechanism of the layered foundation soil. This on the top is a strong soil, and below is a weaker soil. And Professor Meyer and Hanna, 1978, presented this layered soil, the formula for bearing calculation of the bearing capacity. Professor Das' book, Principle of Foundation Engineering book, presented this. And also the Lawton, 2001, he presented the basal reinforced foundation for shallow foundation. And there's various types of the reinforcing system like this, maybe similar to the geocell foundation. So I think this he also proposed the formula for this layered foundation system. So that mechanism of honey cells, I think where we induce the resistance against the surcharge load. This is a block, concrete block, and the first part, the increase of the penetration resistance with the confinement, because with the loading this on a puncture, to the vertical direction. And the second, when in case have a field, the gravel or some granular soil inside of a hollow this part, upon the loading, the vertical loading transport to the lateral load with the coefficient of earth pressure rest, and which creates the shear resistance along the circumference of this part in the hollow part. I think this is the advantage of this, because some other methodology of the reinforcement of shallow foundation, not like this. Without this part, this is all filled, okay, and the different shape, and maybe triangle shape of the cubical cell. Sometimes they use as a basal reinforcement, but which cannot have the internal frictional resistance in the hollow part. And the number 3 is additional confining pressure, and also resistance against the passive pressure, against this failure mode, so that number 3 reduce the failure surface and increase the effective stress below the foundation. And number 4, composite foundation effect with a hollow block and also filled material. So this is a somewhat reinforcement of the basal foundation, maybe like a geogrid or some like a soil cement, the improved area or so on. So this is a failure model, very much looks like the Meyer Hanna but we have here the hollow block, this space, and also the resistance along here, and this is a schematic diagram. And we have also the bearing capacity problem in the bottom soft layer. So we combined this part and this part and this part and the basal part, the four part together. We propose the formula for estimating of the bearing capacity. So that this is a formula Q total. Q sub S is a skin friction inside of the hollow block, and Q sub K is that this part, okay, this part of the this part here, this part of the bearing capacity. And next formula K sub S is this block. This is a block mobilized together against that the surcharge load, and the number Q sub B is an ultimate bearing capacity of soil beneath of the reinforced layer based on the dimension of a hollow concrete block. So we defined each category of this. Of course, we can find out this direct show test, and we can find out the interface friction angle from the direct show test, and we can calculate, overburden pressure, and those Q sub S, and this is the right below the hollow block, and which is a parameter. We can find out all the K sub S like puncture resistance, like the Meyer and Hana, he proposed of that. And Q sub KS is the bottom reinforcement, that is the resistance together with the hollow block area as a one body, like a puncture resistance force in combined concrete modular block and also reinforcement area. And number 4 is the basal reinforcement, and that's the area of reinforcement divided by area of the concrete block. And so that all this is similar to the Meyer 1963 is a general equation for calculation of the shallow bearing capacity of shallow foundation with the consideration of the shape factor, various shape factor and depth factor, and also that inclination, loading inclination factor. Okay, so with the combination of 4 different category, we can add up together to determination of the ultimate bearing capacity by using the modular block, hollow block, the foundation system. Yeah, this is inside of the increase of shearing strength inside the block. As you see that here, the C terms and also the appearance cohesion, and we can calculate this sigma h and the tangent phi. We can find out the shearing resistance. So because this advantage of this, we have a very large area inside of the interface with the gravel and internal and with the additional combined pressure. So increase very much, the resistance against that. Okay, and we monitor the load distribution, and when you apply the load, how much the load is distributed, that lateral load here, and also vertical load here, and also that right below the concrete block. And we measured it by installation of the load cell, and we quantified it. Now, we want measure the vertical stress increment due to the surcharge load on the top, and we install the load cell at different location over here, and then we measure the load increment with respect to the depth, and also we install the load cell at the below of the hollow block side in the different location. We estimate the load increment. I think that things we can do also calculate load increment by the Buzynski equation. And as you see here, conceptual honey cell bearing capacity problem, and upon the loading, due to the vertical load or the load transport to the lateral load, and we create the shearing resistance all along the interface between aggregate and also the concrete block. And also the hollow part, we have a higher resistance because we have a bottom here, we have an aggregate reinforcing part and some puncture and the resistance. And also we have a high intensive vertical load here, so that resistance is much greater this part than other part. Okay, so we measured it also for that. And we move to the static, the bearing capacity test. We have a very simple device with the container, circular container manufactured by the steel. And this is our data log, and we apply the plate load. And the modular block, we use this case is a single modular block, and this is a loading plate on the top, and make a hexagonal here, so that we determine fundamental the soil properties for the sand, the fill material, and the base material, and the crushed stone, and find out by utilizing the large direct shear device, 30 centimeter by 30 centimeter. We found out apparent cohesion and also angle of internal friction angle. And also that I think this aggregate gives a higher value and a higher apparent cohesion. We have 6 different cases. The factory soil we use first series of our test is the sand we use, and the second case we use the crushed stone, which is really used in the field. Okay, and we want to compare with filling the hollow block inside or empty, and also inside with the crushed stone or empty or crushed stone. And we want to find out the difference of the bearing capacity for that. And this is a series of the our test for static loading test. In this case, we use only the one single 40 degree of relative density, and we for the case of second series of our test, the shaking table test, we used 2 different types of the relative density of sand, loose ground, a little bit steeper ordinary, and dense ground. So sometimes we have some coastal line, some liquefaction problem, and also loosening of the ground due to the earthquake strikes. We used I think 0.14 Z. I think this is normal we use in South Korea, but the extreme case, El Centro, 0.22 Z. Okay, so they use for nuclear power plant construction and so on. So we used 2 different G level, and we applied 3 different types of the waves. One is the short period of NATO wave. Another one is a long period of the earthquake wave. Hachinohe, and another one is a mixed one, artificial one. We also created the artificial wave and we applied. Let's see, if we are shaking it, bottom, foundation soil, maybe we may have a superstructure here, okay? Maybe building can move back and forth, okay? How much the deviation will create displacement due to the earthquake and with respect to the height. So in Korea case, we do use 0.015 that ratio with the lateral displacement against the height of the building. And in our case, model building about 30 centimeter. And we specific range of accelerometer 20 meter per second square and so on. Okay, so you will see all detail for that. So that's three different types of the soil relative density. We find out the different angles of the internal friction angle, and three waves, two G's. And this is not a wave. Hachinohe wave is a very long wave. And this is artificial. Artificial is pretty strong, you know, mixing together, and we created this one. We normally use artificial one in South Korea. The situation of South Korea, the earthquake condition, I think on highest, the magnitude of earthquake recently in 5.0, maybe in Incheon area, 2.5 to 3.0. Okay, so it's not very severe, but all the structures, normal structures, we design against the Richter scale 6.5. But the airport and also nuclear power plant, we design very high magnitude. This bottom here, yellow one, is a shaking table. We set up the box here, model box here. I think this is a top. This is a structure for simulate the building. Okay. So this we put in the LVDT, lower part and the top part of the structure, so we can measure the relative displacement, okay, in bottom and top. And here we have a LVDT here, and also we fixed this modular hollow block, and we improved the certain area about this 400 centimeter, 400 millimeter width of the crushed stone at 30 centimeter, the depth of the ground improvement. Okay. So as I said, we put in the load cell on the lateral part and the vertical part. We measure the load distribution for sandy case. And this is, I think, a vertical load, vertical displacement, okay? Vertical pressure. And this one is across the stone. But for the case of the, this is across the stone, yeah. Yeah. Well, for this, this is a lateral load. This is a vertical earth pressure, right? Vertical earth pressure. And this is a lateral earth pressure. Lateral earth pressure for sand cases gives higher value than the I think because of the interlocking, that cross the stone layer. And we, as I said, there's a for case one. So with no reinforcement, we put in the plate load test, and we determined bearing capacity for this. And second case, I think is the field the sand and in the hollow part, and we found out pretty high bearing capacity. 924 compared with this, how much? Yeah, about 3 times, 3 times greater than not reinforced ground, So very much increase, the bearing capacity. And also the blank, without this, I think the bearing capacity is not about 250 or something. So not much increase, the bearing capacity for this case. But crushed stone, that gives a very higher bearing capacity. This is case, no hollow block and empty block. I think it's 1,200. Okay, that's great, that increment because of this, here the basal reinforcement and with the field in the crushed stone and the greatest, the bearing capacity we found out and we tabulated all those results and not only increased with the filling the hollow block with the sand, either sand or crushed stone, very much increase of the bearing capacity. Also, the settlement reduced very much. As I said, due to the interlocking in the hollow block side, increased the side friction, shearing resistance, which take the overburden pressure. So that load is not transmitted to the transferred to the below the ground. Okay, so that's why we decrease settlement very much. This is a great advantage of the reinforcement of that. And then we plotted together. This is a green one. This is the blue one, blue dot, which is gives the highest value of the bearing capacity with the here F. The crushed stone with the block B field. And then the brown one, E, crushed stone, empty block. And the green one is the sand with the field, okay, the B part, okay. I think so. So settlement level is B in a 10 millimeter. And also settlement is a reduction very much, as I said, for particular case for crushed stone, the field, which one is very much, the decrease of the settlement compared with the not field, of the void space, okay. So the bearing capacity ratio we determined based on the non-reinforced case, and the crushed stone part is about 4.31 times greater than unreinforced one, and then this one is for this non-field honey cell, and what sand case is a very great also the bearing capacity. Of course, we can calculate all the bearing capacity for our proposing equation. We compared in the the second author of these papers, that Dr. Lee in his PhD dissertation, and very much similar to the theoretical calculation of the bearing capacity with the model test. This is a measurement of the load distribution. This is a hollow block, inside of hollow block, vertical incline. I think that's hollow block is okay. This is right below the hollow block, about 16 to 18%. But they take the load, and the lateral combining force about more than 20%. They take the load, and concrete part of the modular block right below the concrete block about more than 50-60%. Okay, so altogether about 900. So now you can this is all measurement. You can identify which part is most load they taken care of. Okay, so this part of the concrete part right below, and then this shearing resistance due to the hollow block, which covers it very much, and then in the hollow block side. So I think formula also, the theoretical formula is a consideration of these factors also. Okay, and then let's move to the dynamic shaking table test. And as I said, we used three different types of the uh, relative density, and this is a short period of the wave of NATO, and the displacement, horizontal displacement. I think a loose soil gives the highest, lateral displacement compared with the dense the sand case. Okay, and for this case, the maximum our limit I think 0.015 the times h is about 4 millimeter. So here I think this is a pretty high in the limitation of the horizontal movement, relative movement, and for artificial wave. And also Hachinoe, which gives the higher value because it's a long period of the wave application and with the loose sand. Okay, so and also we measure to the relative density against the horizontal displacement. As you increase the relative density, that lateral displacement is very much decrease. So we need some kind of compaction, to densify. So that's why we use the sand compaction pile or other dynamic compaction for liquefaction potential area in Incheon area and also Incheon International Airport. As you see, for this case, you have a big deviation with the eccentric 0.22z and compared with this. And but Hachinoe, this one wave length is very long, and this is not much difference. But anyway, the displacement is very much decreased with increasing the relative density. And we tabulated all horizontal displacement, and this is 4.5 millimeters limit because of the 300 times 0.015. I think this is a very higher value compared with the Canada and also German code. Okay, it's very strict, for this case. Okay, and normally steady case is h h over 300. Okay, this is a normal case for the temporary brace cut wall, but here we case dynamic case about 0.015 h. Okay, so all except this, so for the eccentric the earthquake case, this is gives a higher value. Okay, but the rest of that, this I think so for artificial, the seismic wave gives the very highest value, but the rest of the Hachinoe and Ofnat is gives the a very small magnitude of the lateral displacement. Okay, so let's move to the field case study. The Samsung, they produce, the computer and many electronic goods. So they are very much sensitive to the dynamic loading and also horizontal, the movement and also bearing capacity. And the original design, this one was the foundation type of the pile foundation here, like this. So we have plenty of pile installation for this case. So that like this, maybe this building is a little bit higher load. So we have here, we very densify of the modular concrete block here, okay? But this layer here, it's not much, surcharge load. So we have a strip foundation type of the modular block reinforced ground, and we successfully implemented. I can see here M value, standard penetration M value. I think this is very soft clay here, okay? But still, we can take care of the load with utilizing the hollow modular concrete block. This construction motion picture, maybe we can show. No, okay. I think we have simulated, this, but this is very simple, construction procedure. As I said, I think this is near to in the Incheon area. We have a lot of soft ground. As you see, we took a photograph. I took a photograph of the side 1, 2, 3, 4, 5 stories building. We have a very congested area. Both sides we have a 5 stories building and the soft clay foundation here, like here. Okay, M value is about 5 or something, 4. Oh, so when you're putting the pile foundation here, you have a very much vibrating of ground. So that creates the consolidation of the clay adjacent building foundation, so which dissipates the port pressure that influence to the building foundation. So building maybe try to incline. So in order to reduce the vibration and also disturbance and the noisy with the pile driving, so we use the adopted honey cell foundation system. As you see, after we installation of the honey cell, we are now the loading test, okay, plate load test, and we found out about 21 ton per meter square. So that greater than the 15 tons, because 5 stories, so about, that the higher, high enough of the bearing capacity against that building surcharge load. And this is another case in history, about the Suwon area near to the Seoul area, about the 5 stories building right here. Okay, 5 stories building here and here, and required 250 kPa. And we found out here M value is pretty soft, 227 or something, But still, we adopted this, the concrete modular block. We supposed to, that put in the pile length 12 meters, but instead of that, we used the honey cell in the foundation system, and we took care of the problem. And sometimes we have 15 stories building, and with 2 floors, underground floors of the apartment complex right here under construction, and that's pretty, steep for, the soil foundation here. I think is good enough here, so that we building of this kind of structure completed without any problem. And there's a various case of the, I think this is a good foundation system, particularly for the 5-story or 6 stories building in the soft clay. But if we have a little bit stiff, N value 20 or 30 SPTM value, then we can have more than 10 stories, 15 stories of the buildings, and we have Jeju Island and many different buildings in the across Korea. So they already implemented more than 400 sites in Korea. I think is a maximum highest building 23 stories building, maximum load 600 kPa. I think a conclusion. Hollow modular block reinforced shallow foundation in soft clay is cost effective and very easy to construct in the very limited area, and with environmentally free condition, like less vibration, noise-free technique. I think that with using the hollow modular block reinforced foundation, which gives the more than 3 and 4 times greater than the unreinforced case. I think it's and also that we propose general equation for estimation of the bearing capacity for reinforced by the hollow modular block, and we compare with the measured value, and we found that pretty accurate. And the vertical pressure with the reinforcing with the modular block foundation, which can reduce about 40% of the load increment, so which increase the bearing capacity and also probable settlement. So hollow block, modular block reinforced shallow foundation is effective against the dynamic horizontal loading. So the horizontal displacement was decreased with increasing the relative density, and also all the value below the limit of 4.5 millimeter Korean design standard. Thank you for listening. I think if you have any question, and you can submit the question via email to me and Professor Javid Atla, and we more than welcome to discuss with you or your questions. Thank you for your listening. Javid, no problem?
No problem. Oscar is the session
Sure.
chairperson. He is going to thank you first.
Yes,
Actually, he is coming. Oh,
Thank you very much. Thank you very much, Professor Shin, for your very interesting, informative lectures. And also, I think is very interesting for us, because we more use piling foundations, but we now understand this, high technology in Korea can use another type of foundations. Very nice, very good
Yes, yes.
information. And also, I think some questions come for you, maybe better send by email
Sure.
to organizing committee. Professor Javid Atalar, it will be better, because it will be more effective. So thank you very much.
Thank you.
Thank you very much, Professor Oscar, for chairing the session of the keynote of Professor Shin. One vice president for Asia of the society, and he chaired to the other immediate past president of the society. That's a coincidence. And thank you, Professor Shin, for your valuable information.
Sure.
Thank you very much.
Thank you for invitation.
Thank you. Thank you.
And now I'm going to invite another vice president of the Society for Europe to invite another past vice president of Africa to deliver his speech. Thank you very much. Professor Ivan Wanicek, I hope you are with us. Good morning, Ivan. We cannot hear you. I cannot hear you. I cannot hear you. No voice yet. Abdullah. The technical people cannot hear you, Ivan. Can you hear me? we cannot hear you. We can't hear you. Yönetmen yardımcı olabilir miyiz? Ivan, we cannot hear you. Okay. Now, talk now, please. We can't. We can't. Can anybody help you where you are? Ivan, we cannot hear you. Okay. Okay. Just maybe what we can do is just you can put. We cannot hear Ivan's voice, but he's the chair of the session. So we'll try to fix for your voice if we can help you, but I can invite the next keynote speaker on your behalf, if you don't mind, Münir. So hopefully we can do it. Hocamızın sesini alamayız.
Hocam hallediyorlar onlar içeride. Şimdi tek link devam edelim demişsiniz.
Efendim?
Tek link, aynı linkten devam edelim
Evet.
demişsiniz. Şu an yayında mıyız hala?
Yayın.
Devam edemeyiz aynı linkten.
Okay. Hepsini koyun üstüne. Hepsini koyun buraya konuşamayan dileriyle. Herkes konuşsun. Hepsinin bütün mikrofonlarını açın. Herkesin burada. Tamam. Açın.
Şu an içeride olanlar.
İçeride olanlar. Evet. Hepsini açın da.
Duyuyordur şu an sizi. Siz söyleyin.
Tamam. Abdullah. Herkesi koy ekrana ve şeyleri de mikrofonlarını da aç lütfen. Evet. Münir yok.
Can you hear me, Chavi?
Yes, I can hear you.
But can you
Münir,
see?
I cannot see you.
Your
camera is not on.
Yes, it's on.
Professor Shin, I cannot see you. Professor Asgar, I cannot see you.
Yes.
Okay, I can see you now. Professor Shin. Professor Shin. Professor Münir.
Yes.
I cannot see you. You close your face.
Oh, I have the camera on, so I don't.
No, it's not on. It's look like off.
Mm-hmm. Yeah, positive. Share video. Okay.
Yes, it's coming.
Okay.
Anyway, yes, we got your picture. At least it's okay. Now, what we will do now, we'll take the other. That's okay. Leave it, Munir. We take a picture now here,
Yes.
and then what we are going to do, I'm going to shift the link because we got 2 hours and 21 minutes, and I'm going to send you a new link, and we start with a new link for you. Yes, Shima, we are going to take you in the afternoon.
Hello, everyone. Yes, hocam, I'm just trying my camera and my microphone.
Okay, but okay, you can stay there. We can take your picture as well. Okay, we are taking a pictures and we are going to shift the links. Okay, Abdullah, can somebody take a picture, please? Can you do it, Anna? Okay, I'm going to send you a new link in 2 minutes. Okay?
Okay.
Sure.
Okay. Ferda, çektin mi sen fotoğraf? Fotoğraf çekebilir misin ekranı? Buradan çekemem ben. Neyse bir şey değil. Okey. Bir link verin bana. Hangi link? Bundan sonraki link.
Göndereceğiz şimdi hocam.
Okay. I'm sending you a new link. Okay.
Eğer ki hayatımızda hiç eğer olmasaydı nasıl olurdu? Size şöyle söyleyeyim. Her şey daha az parlak, daha az yeşil olurdu ve daha az parlak yeşil. Çünkü eğerler ormanların derinliklerinde tek bir kibritle derinlerin kıvılcımını ateşler. Eğerler Nobel ve Guggenheim'ın aklına takılır ve o kodu bu kodu çözerler. Eğerlerle içinizden haykırmak gelir. Eğerler bariyerleri kırarlar. Asla yalnız yürümezler ve aşırı bulaşıcıdırlar. Eğerler aşikardır ve son anda golü atarlar. Eğerler dünü umursamazlar. Robotlarla bile konuşabilirler. Karşı takım soluklanırken oynamaya durmadan devam ederler. Sadece basit bir kelime öyle mi? Hayır. Eğerler asla uyumazlar. Hep daha fazla çaba gösterirler. Eğerler bakar, araştırır ve en beklenmedik zamanda ortaya çıkarlar. Eğerler klonlanarak çoğalırlar. Acaba gerçekten yapabilir misin? Yaptın bile. Eğerler aklınıza girmeye çalışan güler yüzlü şakacılardır. Eğerler kapıları açarlar. Asla kaybetmeyeceklerini bilirler. Ve biraz gün ışığına her zaman hazırdırlar. Her şey bir eğerle başlar. Çünkü eğerler ne zamana dönüşür, ne zamanlarsa şimdi. Ve şimdi nasıla dönüşür. Nasılsa asıl. Eğerler bakış açınızı değiştirir. Eğerler oyunu değiştirir. Eğerler dünyayı değiştirir. Biliyoruz. Çünkü biz eğerlerle çalışıyoruz. Yakın Doğu Üniversitesi.